2022. This is the unit 10 where we are going to discuss about Maxwell's Boltzmann statistics and evaluation of molar entropies and Bose-Einstein statistics and Fermi direct statistics and the difference between the comparison between the three different statistics what Boltzmann and Bose-Einstein and Fermi-Dirac statistics. So, and followed by some of the problems are there in this unit. So, coming to the topic here, the I can discuss. We will be discussing about the deriving the equation of Maxwell's Boltzmann statistics, evaluation of molar entropies, assumption of quantum statistics, and the equation of Bose-Einstein statistics and Fermi-Dirac uh, statistics, and those three differences. What are the comparison between those three differences? So coming to the statistical mechanics, the main aim of the is to understand how the macroscopic properties of materials arises from microscopic behavior of the constituent particles. So the main goal of the statistical mechanics is to understand how the microscopic properties of the materials may arises from the microscopic behavior of the constituent particles. In the previously I have discussed what is macroscopic system. Macroscopic systems are considered in the classical thermodynamics, and thermodynamics are in the equilibrium properties for the system variables upon the it mainly depends on the system dependent. So the energy of gaseous system depends on the mainly the system depends on the temperature, volume, and number of moles gas present in that system. So with that, we are going to study in the thermodynamics. In this, for example, the specific heat capacity and its variation with temperature. So in the statistical mechanics, we are going to discuss about the specific heat capacity and its variation with temperature, the entropy of sample of materials and its relationship with temperature and internal energy. So that we are going to study, and the main one more property is the magnetic property of that material. So here, statistical mechanics explains the relationship between the microstate and macrostate. Uh, it's nothing but thermodynamic state. Macrostate is nothing but the thermal state of any system that is exactly characterized for very small area by the system property such as P, V, T, and U. So that we are going to study in this unit. So Boltzmann distribution tells us how the particles in a system. See the Boltzmann distribution tells us how the particle in a system in a thermal equilibrium are distributed between the energy levels of the system. So how the particles in a energy level, the particles are distributed in different energy. The Boltzmann distribution tells us how particles in a system are with thermal equilibrium are distributed between the energy level of the system. In a system, how the particles are distributed between the different energy levels. So it turns to be basis of many important properties of material. It also helps in understanding the physical significance of concept arising in thermodynamic properties. So it also includes the temperature and entropy, not only energy, and the Boltzmann distribution relies on the number of assumptions and approximation. So that we'll going to be discussing in the later part. And here, first is the Maxwell's Boltzmann statistics. Here we'll be considering a system containing n molecules. So this is the box where the system containing n molecules with the energy, total energy is E. So it is distributed in the different energy level. This is the E naught and E1, E2. So like that, it is the molecules are distributed in the different energy level. And number of molecules, it is denoted by N, and the energy system is E. So it can be written as N is equal to N naught plus N1 plus N2 plus Ni is equal to summation of Ni. That is the equation 33. So that is for the number of molecules. For number of energy level, ಇನ್ನು ಈಗಲೂ ವಾಟ್ ಇಸ್ ದಿಸ್ ಇನ್ನು ಕಳಿಸ್ತಾನೆ ಇದ್ದೀರಾ ರಿಜಿಸ್ಟ್ರೇಷನ್ಗೆ ಓದ್ ಸೆಮ್ ಇದ್ ಮಾಡಿರೋದು ಇನ್ನು ಲಾಗಿನ್ ಬರ್ತಾನೆ ಇದ್ದಾರೆ. ಸೊ is the energy of the different energy levels. So it can be written as N naught is the number of molecules in 0 with the T. T is equal to 0 plus N1 T1 plus until plus NiTi. The summation of NiTi is the equation 34. So the thermodynamic property of the distribution W distribution is denoted by W. Here it can be written as the distribution of molecules we are going to calculate from the equation 35. That is N is the molecules and E is the energy level of the molecule. So that is the 35, and pi is the product of all terms. Taking log on both the sides, we are going to write ln of W is equal to ln of n factorial minus summation of ni factorial. That is equation 36. According to striving approximation, so this is what we are going to calculated in the previous unit. N factorial under 5 factorial. The experimental value 5 factorial is different compared to the striving approximation factorial. So if you put 5 factorial, if you're going to calculate, it will be 5 into 4 into 3 into 2 into 1. So if you put the same, the 5 factorial in this formula, the value varies. Now it is discussed in the previous class. So substituting that in the equation 36, the striving approximation, we'll get the ln of W is equal to n ln of n minus n minus summation of ni ln of I plus summation of ni. So that from that we are going to get the equation 37. And further, at equilibrium distribution, the magnitude of W is maximum. Therefore, W is maximum means dl ln of W is 0. So differentiating on the equation, differentiating the equation 37. So differentiating the equation 37, we get the value of, that is the equation 39, where d ln of W is equal to 0. And further, Equation 39 becomes, that is, becomes summation of L ln of Ni into dni is equal to 0. That is the equation 40. We must remember that the following given system, the total number of molecules N at the total energy remains constant. So the equation 40 and is for the 41 and 42 is the equation which is derived for the constant energy and molecule present in the each energy level. So from that, multiplying the equation 41 and 42 by Lagrange method of undetermined arbitrary multiples of alpha and beta. So in further multiplying by alpha and beta for the equation 41 and 42 by adding equation 40, that is previous summation of ln of Ni into dni, that is equal to 0. From this you are going to add this equation, that is the equation 40 for 41 and 42. We'll get the after evaluating the, we'll get the equation 43, which is the alpha beta independent. So mathematical you should go through this mathematical forms in summation log ln of both sides values ತಗೊಂಡಾಗ we're going to resolve that. Should go through this. Only the thing is how you are going to calculate the Maxwell Boltzmann statistics or other derivation I can explain here. So ln of ni plus alpha plus beta ei is equal to 0. And further substituting, taking ln of ni on the left hand sides, going to value, get the value of minus alpha minus beta ei, and further remaining ln on both sides e can be taken as ni is equal to e minus alpha, e to the power of minus alpha, and e to the power of minus be. So that is the equation 44. And further, to determine the value of alpha, for the following method is adopted, taking the equation 44, and we are going to calculate the value of E alpha. So that is the equation 47, and equation 45 in the equation 44 is the, we'll get the Maxwell's Boltzmann statistics. So keeping this, we are going to calculate the number of molecules present in the different energy level. We are going to calculate, and further deriving this equation, the number of, one second. Yes, oh, sorry. And the assumption made by Maxwell's Boltzmann statistics here. What are the assumptions after deriving this? He has told here means molecules are assumed to be identical or distinguishable. Molecules may be similar or it can be distinguished. So Stirling approximation also is applicable in this Maxwell-Boltzmann statistics, and the molecules of the gas are supposed to be ideal, and energy level I for all the molecules may have the same energy EI, but the energy may be arranged at different ways for different molecules. For example, GI number of possible distribution of energy is given by energy level, and this is the degradiency factor. These three are the assumptions made by the Maxwell's Boltzmann statistics. And next is the illustration of that derivation. So let us consider a system containing, you have taken an example and discussed here. Let us contain system containing 100 molecules having the velocity of c, that is equal to root of 51. C square is the 51. But the velocity component of different molecules may be different. So here we are going to take in the six different ways where in the three direction of x, y, and z axis, the velocity may vary for each molecules. Here we are taken for six different ways. For number of molecules, 10 molecules will be in the axis of in the C. If you take this one as the x-axis, y-axis, and this the z-axis, if 10 molecules will be in the velocity will be in the direction of x-axis, and one will be in the y-axis, and one more is in the z-axis. So it may vary. So for number of molecule 15, which is having in the different directions. So here probability factor for complication of 6 in the distribution of velocity among different components. There are the system said to be six-fold degeneration statistical analysis. So GI is nothing but the statistical weight factor. So the equation 49 from the previous, it can be calculated here by writing, there is the equation 49 what we have taken and be written as further Ni is same. It has GI GI is nothing but this GI is nothing but the statistical weight factor. So the further the denomination of sigma summation of gi e to the power of beta e in the expression 49 is the sum of the factors. So it's nothing but the statistical weight factors. It's applied here, and the system which is having the velocity in the three directions, that is x, y, and z. So from the 48 equation, it can be written as Ni is equal to Na of e to the power of beta ei divided by summation of e to the power of minus beta ei is equal to that we can be written as n into e to the power of minus beta ei divided by q. That is the equation 51. taking log on both the sides. So that is the equation 52. According to Boltzmann Planck equation, S is equal to K ln of W, or S by K is equal to ln of W. From the equation 37, we have ln, that is the equation 37 is nothing. This is for the String approximation, what you are derived. Uh, from that, substitute in the equation 52, in the equation 54. Substitute the equation 52 in the equation 54. So we get S by K is equal to N ln N minus summation of Ni into ln of N minus ln Q minus beta Ei. So further substituting, we'll get the equation 55. Here nothing but we are going to calculate for the Boltzmann-Planck equation. So that yes, we are going to get it derived from the equation 54. That is the equation 55. What we are getting? The Boltzmann-Maxwell equation, Planck's equation. So further differentiating the equation 55, we get the equation 56. But Q is equal to summation of e to the power of beta E1. That is the equation 57. What we have got from the equation 56, and differentiating with respect to beta at constant volume. So we get E is equal to summation of Ni Ei, or summation of Ei is equal to E by N, and that is the equation 59. Substituting in the equation 59, these are the mathematical steps you should go through this ಅಷ್ಟೇ. ನಾನು ಹೇಳಿದ್ರು ಸುಮ್ಮನೆ ಬುಕ್ ಓದ್ದಂಗೆ ಆಗುತ್ತೆ ಅಷ್ಟೇ. And further, from the first law of thermodynamics, substituting in the value of dq by d beta in the equation 56 for the first law of thermodynamics, where dq is equal to d plus p dv. So that is the first law of thermodynamics we are going to apply here. And further, ds is equal to dq by dt, or dq is equal to t dvs. That is the equation 68. Comparing the equation 62 and 63, we get tds is equal to de plus pdv. And further, this you need to practice just any equations in Makala. What are the important topics we'll get to know later. And hence the Maxwell-Boltzmann equation becomes, that is the where equation 70, that is the Maxwell's Boltzmann distribution law. For evaluation of, next is the evaluation of molar entropies. So here the distribution of molecules into groups such that N naught are in the group 0 and N1 are in the group 1. Then the thermodynamics probability of W is given by W is equal to N factorial of divided by N naught factorial into N1 factorial. That is the equation 71. And evaluation of molar entropies. For here, the expression has been derived from the classical mechanics. For degree of energy level, Here that is A for degeneracy of energy level. Degeneracy is nothing but the process of that energy level, and that can be written as the equation 72 W is equal to n factorial. Continued. And for B, for the indistinguishability of molecules, means it cannot be distinguished. So that for that molecules we are going to calculate from the equation 73. So for the here you should be knowing what is the degeneracy. Degeneracy is nothing but the process of that energy level. So and one more is the indistinguishability. So indistinguishability is nothing but it cannot be distinguished. So for the indistinguishability of the molecules, which is done by dividing equation 72, is the n factorial. So further W is equal to, we can get the number of indistinguished molecule. I mean in the equation 73, taking log on both the sides. For the equation 73, taking log on both the sides, we will get the summation of ln of W is equal to followed by n fact not ln of G naught. And further applying steric approximation, there is a formula n ln of this previously I discussed where it is. The previous unit ಅಲ್ಲಿ the steric approximation the formula. I will explain there itself, otherwise you'll get confused. Yes, this is the steric approximation where ln of n factorial is equal to n ln of minus n. That is the equation 11. That is the steric approximation. So it is the approximation of the system containing a very large number of particles or molecules. So approximation of the system containing very large number of particles or molecule, that is known for steric approximation. So that formula we are going to take it in this equation. Yes, here that is first applying steric approximation. So ln of summation of ln n I factorial is equal to summation of ni ln minus summation of ni by applying steric approximation. Further substituting in the equation 74, this value what we have got, this value we are going to substitute this in the equation 74, and further ln of W is equal to summation of Ni continued. That one we are going to get according to Maxwell's Boltzmann distribution law. Ni is equal to, in previously we have got the Maxwell's Boltzmann distribution law. That is the equation 70. Ni is equal to n into Gi into e to the power of e minus ki divided by kt divided by whole divided by q. So for that, taking the log on the both sides, we'll get the equation 76 by applying the equation. This equation will get the equation 76, and further substituting the equation 76 in equation 75. So substituting the equation 76 andre nothing but we are going to take the value of this in the equation 75. For equation 75, where it is? Yes, this one. So further we'll get this we have been substituted, and next we are going to get the n ln of q divided by n plus e divided by kt plus n. That is the equation 77. Further, in the replace of e is equal to kt square into d ln of q by dt. So that we are going to replace in the equation 78 with the value of e. So this is the evaluation of molar entropy. Further, quantum statistics. Here, Maxwell-Boltzmann statistics also called as classical statistics. Particle distinguishable and any number of particles can occupy any energy level. So, according to Maxwell-Boltzmann statistics, the particles are distinguishable. The particles can be distinguished, and any number of particles can occupy any energy level. So, particle with zero value of spin, which requires the overall wave function symmetrically. The wave function whose sign does not change. Also, the wave function. Where we are going to calculate the velocity of that particle, and these are called bosons and they obey Bose-Einstein statistics. So here bosons are nothing but these are the particles that carry energy, bosons which carry particles that carry energy and force through the universe. So bosons are nothing but the particles which carry energy and force through the universe. For example, they are given photons, deuterons, and nuclei of the atoms. So these will be interacting inside the system. Next is the particle with half integral values, means half spin, where it can require overall action to be symmetric or antisymmetric in the wave function changes. So here the particles are Fermion and they obey Fermi direct statistics. So, for example, electrons, proton, neutrons, and nuclei of the atoms of the odd molecules. And Boltzmann distribution equation is applicable to distribution of particles in a system containing gas or low density. So, it can be applied. Boltzmann distribution equation can be applied in the particle in a system containing gas or at low density. With high pressure, it also fails to express distribution of particle system containing gas at high density. So only gas at low density it can be Boltzmann distribution equation can be applied. So it leads to the deviation of so for this drawback it leads to the other two uh, distribution equation have been derived by Bose-Einstein and Fermi-Dirac equation. So other two from apart from the Maxwell's Boltzmann statistics, there are another two derivations such as Bose-Einstein and Fermi-Dirac equations. Because it fails to explain the distribution of particles in uh, gas at low density. So coming to the next topic is the Bose-Einstein statistics. Here N is the molecules. It is the sorry, N is the indistinguishable particles that consists in the system divided into a series of quantum groups. So N is nothing but the particle or molecules and each group having energy E0, E1 respectively. Both even this is having the molecules N, N0, N1, N2 in different energy level. So the total number of particles and total energy of all particles present in the system are in constant. So here let the G1, Gi is nothing but the degradation energy level. So the equation 80. Here we imagine the box uh, or a system divided by Gi minus 1, where partition into Gi section. Gi is nothing but the degenerated energy levels. So the energy level which is degenerated energy level that is denoted by Gi. So Ni is the particles that suspended in distribution among the section. So here Ni is the particles suspended in distribution among the section. So the total number of permutation of Ni particles in Gi that is can be written in the W is equal to pi into Ni plus Gi minus 1 divided by Ni factorial into Gi minus 1 factorial. That is the equation 80. So the thermodynamic probability of the distribution of particles among the various energy levels that is given by the equation 80. And here the Ni particles are indistinguishable and the permutation among the particles means from one energy level to another level. So there will be a permutation of the particles among the energy, different energy levels. So total number of and particles, sorry, the total number of particles is divided by Ni factorial and the permutation among this uh, can be G minus I, which is G minus Gi minus 1 partition, which varies. So further, the pi represent the product of the similar terms. Taking log on both the sides, you will get the equation. Uh, this and further Stirling approximation I had told where ln of Stirling by applying Stirling approximation that is nothing but the ln of n factorial is equal to n ln of n minus n. That is the in the equation 11. That is the Stirling approximation. So from that, applying in the above equation, we get ln of W is equal to summation of Ni plus Gi ln of Ni plus Gi minus summation of Ni continued by summation of Gi minus summation of Ni ln of Ni. So this is the after substituting in the Stirling's equation, you will get the equation 81. That is with respect to Ni, number of molecules in different energy levels. So it can be further written as d ln of W, where summation of ln into 1 plus Gi into dni, that is the equation 82. Further equilibrium distribution, where W is equal to 0 and summation of ln into 1 plus Gi divided by ni into di, that is 0. We have summation of that. If I start telling all the equations, it will be like reading. We go through this the mathematical section. So we'll get the equation 86. In this, the mathematical represent the Bose-Einstein statistics. So what are the difference between the Maxwell-Planck, Bose-Einstein, and for me, direct statistics will be discussing the difference of comparison between all these statistics. So we'll go get into the next topic is the Fermi direct statistics. Here, Maxwell's and Bose-Einstein equation was no restriction on the number of particles in a given energy level. But in Fermi direct statistics, only each molecule should be present in the each energy level. So only one molecule will be present in each energy level. So in Fermi direct statistics of particles, the division will have to be done in, according to this principle, no two electrons in an atom can be same energy level. So this is what they explained. No two electrons can be present in the same energy level. Only one electron should be present in the each energy. Hence, not more than one particle can be assigned to particular energy level. So W is equal to pi of Gi factorial divided by Ni factorial into Gi minus Ni. That is the equation 87. So taking log on both the sides should be given ln of W with respect to summation. Applying the Stirling approximation where ln of n factorial is equal to n ln n minus n. That is the Stirling approximation. So it can be written as by applying Stirling approximation. The summation of Gi ln of Gi minus summation of Ni ln of Ni minus, that is the equation 88. Further differentiating, we will get the equation 89. And for distribution where W is be 0, D ln of W will be 0. When it is equilibrium of distribution, it will be 0. So keeping W is equal to 0 or D ln of W, that is 0. We are going to include in the equation 89. That is the 90 we are going to get. Further, we have summation of dni is equal to 0. Summation of E1 dA EI into dni is also 0. By multiplying the equation 92 and 91 by beta and substituting in the equation 90. So this is the equation 90. What we are going to substitute the value of 91 equation and 92 equation. That will get the value of in the 93 equation. Further, inserting this equation 93, we get Ni is equal to Gi divided by beta e to the power of Ei by kt plus 1. That is the equation 94. So here the most probability distribution Ni individual particles among various energy levels, that is shown in the Fermi Dirac statistics in the equation 94. So first we are going to go to the comparison between these three: Maxwell's, Boltzmann, Bose-Einstein, and Fermi-Dirac statistics. What does they say here means the particles are distinguishable in Maxwell's and indistinguishable in the Boltzmann-Einstein theory and indistinguishable in the Fermi-Dirac statistics. So next is the derived on the basis of classical mechanics, and these two are derived on the basis of quantum mechanics. And there is no restriction on the number of particles present on each energy level, and even in the bone sensing also there is no uh, restriction for the number of particles present in the each energy level, but there is a restriction in the Fermi Dirac statistics where one particle per energy level. So applicable to particles which are ideal, applicable to bosons. Bosons are nothing but the particle that carry energy and force through the universe. That is the bosons. And bosons, if you, what are the examples I told earlier for bosons? Consider bosons in statistics. And so in the bone science in statistics, maximum, yes. Bosons, for example, for bosons, it can be photons, deuterons, and nucleons of the atoms. So those can will be under the Bose-Einstein statistics. It comes under the, and the bosons are nothing but the particles which carry energy and force which throughout the universe. So some of the examples of bosons here can be photons, deuterons, and nuclei of the atoms of mass number. So that is what from the Bose-Einstein and Fermi Fermi Dirac were applicable to Fermi ions. Fermi ions are nothing but the particles that flows from Fermi dielectric statistics. So these are the particles that flows from the Fermi dielectric statistics. And next is there is no symmetry restrictions, and there is a symmetrical restriction, and it is a anti-symmetric in the Fermi dielectric statistics. So these are the three form derivative formulas were derived for the Maxwell's for different statistics. So this is for Maxwell's, Boltzmann, and Bose-Einstein. This you should be keeping in remembrance because some of the problems may given for Maxwell, Boltzmann, or Bose-Einstein or Fermi dielectric statistics. So coming to the problems here, for first one we are going to calculate the number of ways of distributing three distinguishable molecules between three energy levels. So the molecules are distributed in three energy levels. So energy level is occupied by each molecule. What we are going to take n factorial is the n3. So n is the number of molecules, that is 3, and E is the energy level. So we are going to calculate W is equal to n factorial divided by n naught, n1, n2 factorial. So that is we are having three molecules, 3 divided by 3 factorial divided by 1. In each level it is substituted in one molecule. So n naught will be 1 factorial, n1 will be 1 factorial, and n2 will be 1 factorial. So that is 3 into 2 into 1 divided by 1 into 1 into 1, that is 6 answer. And for identical particles that are distant between the two identical containers, that each container has two particles. What are the number of possible arrangements for distinguishing and indistinguishable particles here? For distinguishable particles, W is equal to n factorial by n naught into n1 factorial, where 4 is the number of molecules. In n naught factorial, in the first level, N naught, it will be two molecules. In the second, it will be N1, there will be two molecules are present. Total four molecules are present means in the two energy level, two molecules will be presented. That is what here they are given. 4 into 3 into 2 into 1 and divided by 2 into 1, 2 into 1, where the answer is 6. And next, W is equal to, we know that for indistinguishable visual, for distinguishable we have made, for indistinguishable particles, W is equal to 2 square divided into 2 square divided by 2 factorial into 2 factorial, where 4 into 4 divided by 2 into 1 into 2 into 1. That is the 4. What we are going to for the indistinguishable molecules. For next is the problem 3, distribution of two particles in three levels for the following Bose-Einstein and Fermi dielectric statistics. So for Bose-Einstein, we are going to take this formula where we will be writing W is equal to Ni plus Gi minus 1 Ni factorial divided by Ni factorial into Gi minus 1 factorial. So given number Ni having two molecules, Gi the volume of degradation, where W is equal to 3 factorial divided by 2 factorial into 3 minus 2 factorial. This one we are going to substitute the values in that formula. The value is 3. So calculating the number of ways for distribution of two fermions among four energy state. So here we are having only two ions. It should be distributed in the four energy state. So here we have the formula W is equal to GI factorial into, that is the formula here what we have got, this one, for Fermi direct statistics. That one we are taking here, and 2 we are going to Ni is equal to 2 we are going to substitute, and J is equal to 4 we'll get the result if you are substituting that. And next is the obtain the probability distribution for system of four particles distributed in such a way that two are in E naught and none in E1 and one each in the E2 and E3. So how much molecules will be present? Two in the E naught means two ions plus none in the E1. There is zero in one E1, and E2 and E3 it will be having four. So any total number of molecule is nothing but the four molecules. Here from the question itself, see here, such a way that two are in E naught. So two molecules are present in E naught and none in E1, that is zero, and one each in E2 and E3. So E2 and E3 will be one on the other, means so two plus two in the E naught, it will be four. Total number of N is equal to four. N naught to that. So in the energy level, two molecules at zero energy and one zero molecules at one energy level, and one molecule at N2 and one molecule at N3. So that we are going to substitute in the equation. W is equal to n factorial divided by n naught n1 into n3 factorial. So if you substitute those value, you'll get the answer 12. So these are the problems what you are given. Simple problems ಏನಿದ್ರು values questions ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕು, number of molecules, energy level. So we are going to substitute that in which energy level how many molecules are present. That one if you get to know that, and you should be remembering these three formulas where for Maxwell, Boltzmann, Bose-Einstein, and Fermi direct statistics. This one you should be remembering, and basic n factorial you should be remembering these four formulas. And this is the end of the unit, and this is the summary. If you go through the summary, you get into know the whole unit. What is the concept of explaining the whole unit? Aಷ್ಟೇ. End of this unit. Next class, next unit on. If there is any doubt, let me know.